right. There was a question on the discussion board about the homework. I answered it just a moment ago. In the homework, you're asked to make some pictures with the onset data. In particular, you're going to make a picture of age versus onset. And when you make the picture, you'll see that there's kind of two distinct patterns. And those really pop out whenever you add a smooth curve that is specific for the different prior groups. There's a curve for prior equal, I think this was the prior equal 1 case. And there's a curve for the prior equal 0 case. Something like that. In making the curves, I asked you in the homework to use the smooth.spline function. Let me get a script open. Okay, I'm going to start a new script and just illustrate a simple case. Let's simulate some data, make a scatter plot, and overlay a smooth curve. I'm going to make some random normal data first. R norm, give me 100 observations, say. I'll leave it default choices for mean and variance. That will give me mean 0, variance 1 by default. And then let's say that y is 2.5 minus 1.2 times x. This is like saying we have a linear regression model. I simulated some covariate values, x's, and then I used those in the following equation to say, let's make y be linearly related to x. Intercept is 2.5, slope is minus 1.2. To make y like actual observed data, we can add some random error. So this will look very familiar soon because we'll be talking about linear regression. You don't need to know about the details right now, but what I'm doing is just simulating some data. Let's say R norm 0, we'll do standard deviation 0.5. Just making up numbers and going to use them to simulate some data. So now I have 100 x's, 100 y's. And let's make a scatter plot of them. Scatter plots can be done with the plot function. What do you want on the horizontal axis, comma, what do you want on the or the vertical axis? This just puts points. Now let's add a smooth curve. Let's make this an actual curve, because I currently just have it as a line. So let's say minus 1.2 times x plus 0.5 times x squared. Now when we plot this, we should actually have a curvy looking relationship, like that. Now let's add a smooth curve. There is the smooth.curve function. And if you call smooth.curve, you can ask, or you can specify what you want in the same way that you did with the plot function. So I'm going to say smooth curve x comma y. Let me double check that I got that right. Question mark smooth dot curve. Smooth dot spline. Splines are mathematical ways of representing smooth curves, arbitrarily smooth curves, where you have a parameter, like degrees of freedom in this case. You have a parameter that you can use to gauge or to restrict how wiggly the function can be. Smooth.spline. Okay, so all I need to do is say x and y, just like we did with the plot function. Smooth.spline x comma y, and let's just leave it like that and see how it looks. Okay, when I say smooth.spline, it computes the goodies that are necessary to do the smooth.spline, but it doesn't actually draw it. So if I want to add the curve that was computed by smooth.spline, I'm going to use the lines function. Lines overlays a curve on an existing plot, just like points overlays points on an existing plot, and text overlays text. Let's do lines. Okay, and it looks like that. The way that you can control the wiggliness of the curve is with the df argument. So if I said smooth.spline x comma y, but then I specify df, let's let it have lots of degrees of freedom. Lots of degrees of freedom would say you can be very wiggly. What does it look like if I do df equal to 10? Let's make this one red. It's a little bit more wiggly. What if we make it wigglier still? How about 50? Okay, now too wiggly, nearly interpolating the plot. So think of a smooth spline, a smooth curve, a smoother. There's different algorithms for doing them, but all of them have similar features in that they're going to let the data decide what the curve looks like in a local way, allowing it to be curvy with restrictions that it's a smooth curve at the end of the day, or at least a continuous function at the end of the day. When you apply smooth.spline to the onset data, the comment on the discussion board was that he was getting a jagged curve like this. You don't have to, or I didn't tell you to specify the degrees of freedom in the smooth.spline function, but my response to that issue that he was seeing, that Derek was seeing, was to specify a small df, relatively small df. If you don't specify it, it's going to use some kind of rule of thumb to guess what df do you want. All right. So to make your curve smoother, you can pick a small df, 3, 4, 5. Okay, so what are we going to do today? This week, my goal is to finish our discussion of, or basically finished with our discussion of the simulation-based inference. Basically, bootstrap. Bootstrap, a general way to approximate sampling distributions for an arbitrary statistic. And sampling distributions of a statistic, that's how we do inference. So one way to do inference, bootstrap. And we'll see it repeatedly throughout the semester. We'll apply it to correlated data. We'll apply it to survival analysis data, certainly regression data. And briefly, since I think you know this material already, or at least you've seen this material, I wanted to fill in where what I'm calling classical methods fit in. If you can use the bootstrap to do confidence intervals and hypothesis tests, that's one way to do inference. Stats 101 would have taught you a different way, most likely, and that would be t-tests. On Friday, we're going to see yet another way, which is Bayesian approach. All three of those are approaches, valid approaches to doing inference based on sample data. So let me just write a few things here. Again, I think you have seen these things before, but perhaps by putting them in a condensed form with the appropriate background understanding, you'll understand them a little better. First off, let's suppose that we have, I don't want green. Let's suppose that we have a sample of observations from some population. So we have x1, x2, ... xn, and these are a random sample, which means they are all independent and they all came from the same distribution. We can call that IID, independent and identically distributed. They all came from the same distribution, and let's call that distribution F with a subscript theta. Theta is a collection of parameters. If you tell me the parameter values for this population, we can compute probabilities of seeing data like ours. F theta is the probability in the population. For example, it could be normal. We could say I have a random sample from a normal distribution. In that case, the parameters would be mu, the mean, and sigma squared, the variance. But just arbitrarily, let's say we have a random sample from some probability distribution. Then a way to go about doing inference is called maximum likelihood. And it gives rise to the things you know of as t-statistics, t-tests. How do we do this maximum likelihood idea? The idea is to say we observed some data. That's what we have to work with. We think that there is a particular probability distribution that holds in the population. So this is already different from the bootstrap. Bootstrap didn't say anything about the population distribution. Right now we are making an assumption. Let's assume our data are normal, for example. If we did that, if we said that this is the probability distribution, then we can write down a quantity called the likelihood. And roughly speaking, I'm going to talk in rough terms. This is not exactly true, but the likelihood, you can think of it like the probability of seeing our data when, or let's say for, with parameter values theta. We have our observed data. We're going to construct this function of the parameters and ask for different choices of the parameter values, what is the estimated probability of seeing our data with those parameter values? It's not exactly the probability, but it is, think about what we do with, say, probability. Let's back up just a second here, and let's say that U and V are random variables. This is basic probability. U and V are random variables. The joint probability, let's say the probability that U takes a particular value little u, and V takes a particular little value V. Joint probability that simultaneously you have these two things. If U and V are independent, that's a statistical relationship, independent. If they're independent, what that means is that, for example, the probabilities that apply to U, the random variable U, do not change when V changes. If they are independent, then we know, for example, U equal U, the probability of that, given that V equals little v, is the same thing as what we call the marginal probability that U equals U. Also, we have that the probability, the joint probability U equals U and V equals V, is the product of the marginals. You can factor a joint probability when you have independent random variables. So if I wanted to ask, okay, here's U and V. I observed values for these two variables. What's the probability of observing these two numbers simultaneously? If U and V are independent, as they would be if these were draws from a population. If we have a random sample, every number in our data set is independent of all the others. When we have that, the probability of seeing our data, that's like a joint probability. For a particular choice of theta, what's the probability of seeing these n numbers? So that would be like a joint probability, but because we have independence, we can product. The likelihood is defined as a product over the individuals of the probability function evaluated at each xi. The likelihood, the way you compute it, is you compute, first we assumed a distribution. Might be normal. F theta is some distribution that we wrote down. We're postulating a distribution, and it has parameters referred to by theta. The likelihood is, what's the probability function of seeing x1 for that choice of theta? What's the probability of seeing your x2 for that choice of theta? And to construct the joint probability of seeing your data, you product them because of the independence. All right, I need to speed up here. But what I'm about to say is, let's assume, let's look at the normally distributed case. We wrote a couple of slides ago that the likelihood of theta is product, I equal 1 to n, of f theta x I. Another way to think of this, well, okay, we'll stick with what I've said. Think of the likelihood as a function of theta, a function of the unknown parameters. We're going to vary theta and ask which values are most consistent with our data. This is an inductive kind of reasoning. We're asking which values of this are consistent with the observed data we saw. Okay, let's say one more thing here. The likelihood is this. And what this gives us is a natural way to go about estimating theta, because we don't know what it is. It might be a population mean. We don't know what that mean is. We need to estimate it. So maximum likelihood estimators, what we call the MLE, maximum likelihood estimator, of theta, call it theta hat, is the value of theta that maximizes the likelihood. All that means is find the value of theta that made that capital L biggest, which is sensible. What is the population mean what is the population mean? I don't know, but I could ask which value of the population mean would fit our data best, basically is what we're doing. Which one would make it the probability of seeing our data highest? So let's consider an example. Let's suppose that we have normally distributed data. So x1 through xn are IID, normal with a population mean mu. And for illustration purposes right now, we're going to say a known variance. So I said sigma squared 0. By that I mean it's a known quantity. Based on prior data, prior research in this area, we saw data with which we estimated that to be such and such. So we're going to treat it as a fixed quantity. In this case, the likelihood is known. Since we specified a probability, a specific probability distribution, all I need to do is product up the normal PDF. So I have something you would look up in your textbook to remind you, e to the minus 1 over 2 sigma squared 0 xi minus mu squared. That's the normal PDF. And what we would do in practice is, if I wanted to do maximum likelihood, what I want to do is pick, in this case, mu. Mu is the only unknown parameter, so let me clarify that over here. Mu is the only unknown parameter. The way I would pick mu hat is to optimize or maximize this function, which is calculus. So differentiate and set to 0 kind of thing. It turns out it's easier to do if you log transform first. The log of a product is the sum of the logs. And so I'm just going to write what we had up above. E to the minus 1 over 2 sigma squared 0 xi minus mu squared. So a log likelihood is what we could work with. And I won't do all the calculus or the derivative. I don't expect you to do derivatives on our exams. But the idea is we want to maximize capital L of mu. And the way we would do that is differentiate capital L of mu, or equivalently little l of mu, set that equal to 0, and solve for the value of mu that achieves that maximum. It turns out that in the normal case, after we differentiate set to 0 and solve for our estimate, the estimate mu hat is something sensible. Works out to be x bar. So it's not that hard to do this. If you log transform, this expression becomes simpler. Just differentiate with respect to mu, set it equal to 0, and you'll see maximum likelihood estimator of mu is x bar. That's not surprising, but this was an illustration of how this idea of maximum likelihood works. Suppose we had a different distribution, not normal. Suppose we had totally different parameters that we wanted to estimate. As long as we can write down a likelihood, we can either analytically or computationally try to maximize it to get good estimators. So how are these estimators good? There are some nice properties of MLEs. I'm not going to show an exhaustive list but I'll show a couple of things. One, MLEs are what's called consistent. That means that theta hat converges to the population value as your sample size gets big. So with a big sample size, you're confident that your MLEs are good estimates. They're going to tend to be close to the truth. And something else that is extremely important for us is that the maximum likelihood estimator is at least approximately, and this approximation is driven by sample size also. The bigger the sample size, the better the approximation that says MLEs are normal. Mean is the truth, and in our case, some mean, the expected value in the parameter, and then there is a variance of the maximum likelihood estimator, which is some quantity. I'm not going to go into it, but it can be estimated. Generally, if you specify a likelihood, a probability distribution, you can use either math or an algorithm to get estimates, theta hats. And you can get an estimate of this standard deviation of your estimate. That's a standard error. If you have an estimate and a standard error and the actual distribution, you're ready to do inference, confidence intervals, hypothesis tests. So this approximation holds if you have a large sample size. So what does that get us? Suppose that we want to do a test to test null hypothesis that theta equals some particular value. Based on the results for MLEs, we get to do t-tests, basically. So test statistic that we're going to look at, a test statistic is just a statistic, and a statistic is just something you compute on data. A test statistic specifically is a number you're going to compute that quantifies how different your data are from the assumption of the null hypothesis. Test statistics will tend to get extreme when the null hypothesis is not true. In this case, the test statistic for an MLE that we could use looks like this. And this statistic is approximately standard normal. Remember that if you have any old normally distributed random variable, let's say this is normal with mean mu and variance sigma squared. If you standardize it by subtracting its mean and then dividing by its standard deviation, you get standard normal, normal 0, 1. So down below, we said theta hat is approximately normal based on the properties that we saw. So if I standardize theta hat by subtracting its mean and dividing by its standard deviation, we should have approximately standard normal. Notice that the standardization operation, like the u minus mu divided by sigma, that would only be standard normal if I subtracted off the correct mean, mu. Like, for example, suppose u is normal with mean 0 and variance 1. It would look like bell-shaped curve centered at 0 with a spread of 1. Suppose I tried to standardize u by subtracting off what I thought was its mean, but is not actually its mean. Instead of the correct thing to subtract off, I subtracted off a 1. This will not be standard normal. In particular, because I subtracted off the wrong number, these are going to tend to be negative numbers. So the point of that little blurb right there was I'm trying to emphasize the way we're constructing the test statistic. The test statistic looks like it's of the form estimate the parameter that you're interested in, subtract off what you think that parameter's value is under the null hypothesis, and then divide by the standard deviation of your estimate. This kind of statistic, it's a general way of doing a test. It has a special name. This is called a Wald test. When you do MLE, then because of the large sample properties, if you have a reasonable sample size, you can always test a parameter by doing a Wald test. Estimate minus null value divided by SD of estimate. That would hold if we had a single mean. That would hold if we had a difference of two means, a difference of proportions. Any MLE can be the basis of inference, large sample style, using a Wald test. Okay, so this subtracting theta 0, why are we subtracting the value of the mean under the null hypothesis, or the value of theta under the null hypothesis? The reason we do that is because of the approach to hypothesis testing. The way that we do hypothesis tests is we formulate our research question into two competing hypotheses, null and alternative, and we assume, so let me write this down, we assume that the null is true. To test whether theta equals a particular value, we formulate the null and alternative. So the null is that theta takes a particular value. You always pick a single value for the null hypothesis. That's because what we do to get a p-value is we go to the sampling distribution that would hold when that is true. There needs to be a value so that you can go to the sampling distribution. These are our hypotheses, and we assume H naught and ask how, roughly speaking, how consistent our observed data are with that assumption. Okay, that's the strategy. Assume null is true and ask, do the data give me enough evidence to reject that assumption? The next step, once I've written down my hypotheses, null, alternative, the next step is to define a test statistic. We're going to collect some data, and based on the data, we need to compute something that gauges, is the data consistent with the null or not? When we compute the test statistic, that Wald statistic, we did theta hat minus theta 0 divided by the standard deviation of theta hat. That's the Wald style statistic. The reason that it looks specifically that way, we standardized theta hat, and when we standardized it, we specifically subtracted off the null mean. So if the null hypothesis is true, and only if the null hypothesis is true, but if it is true, under the null hypothesis, That's when we have standard normal. So it escapes many students as they're learning statistics, but everything is driven after having made the initial assumption that the null hypothesis is true when we do tests. Assume it's true, then compute a statistic that gauges whether that's consistent with your data or not. Okay, very briefly, let me just show you how this translates to your familiarity tests. Suppose initially we're going to do inference on a single proportion. Let's start with proportions. We have data Let's say we have Bernoulli data, success-fail data, x1, x2, xn are independent, identically distributed from the Bernoulli with probability p. Bernoulli is what happens when you flip a coin, for example. Each trial is either 1 or 0, success or fail. And p is the probability of success each time. This could be like the NFL data set that we saw. We had 16 games. Each one was either win or loss, 0 or 1. A valid probability model that would enable maximum likelihood estimation and inference would be a Bernoulli, because that's exactly what the Bernoulli does, success, fail, for independent trials. So in this case, we could compute a likelihood. The likelihood as a function of p is the probability of seeing these in zeros and ones. One way to do that would be product I equal 1 to n, p to the xi, 1 minus p to the 1 minus xi. If you went through all the x's, each x is either a 0 or a 1. If x is 1, then the contribution to the likelihood for that individual is p to the 1 times 1 minus p to the 0, or just p. That just means the probability of a success each time is p. For all the people or individuals for which x is 0, you have p to the 0 times 1 minus p to the 1. So it's 1 minus p. This is Bernoulli probability distribution. So the big picture right now is we have a likelihood, and therefore we would have a log likelihood, and we could either do calculus or throw an algorithm at it to pick p hat that maximizes this likelihood. We already know what it is. We've seen it in a previous discussion. The MLE of p is the sum 1 over n, sum I equal 1 to n xi. It's like an x bar. It's a sample. It's like a sample mean of zeros and ones, which turns into a proportion. That's the MLE. So suppose we wanted to do inference on p. We have a sample of n zeros and ones. What is the value of p for this population? What is the probability that the Houston Texans win any given game, for example? Suppose we write down a null hypothesis that p is equal to a particular value, and an alternative hypothesis that we'll say for now p is just not equal to that value. The test statistic, Wald style test statistic, would be estimate the parameter of interest, that's our MLE, it's our estimate, minus the value of the parameter when the null hypothesis is true, divided by the SD of the estimate. And the SD of the estimate p hat minus p0. I'm just going to write it down. You can review your Stat 101 book, but what we end up putting down here is p0, 1 minus p0 over n square rooted. Under the null hypothesis, the variance of a Bernoulli, expected value of any one of these is p, and the variance of any Bernoulli is p1 minus p. So down at the bottom, the denominator of that statistic comes from that result for Bernoulli's. But long story short, here is single proportion. You want to do inference on a value on a parameter p. The way you can do it, one way, is maximum likelihood. That gives rise to this test statistic, and under the null hypothesis, if the null hypothesis is true, this is standard normal. So you could get a p-value by putting your test statistic up against the standard normal and computing a tail probability. Right. That's one proportion. Let me very briefly fill in what it looks like for a mean. Inference on one mean, mu. So suppose now we have a random sample from, let's for now say some distribution. Independent and identically distributed from some distribution, but I'm not necessarily saying what that distribution is yet. We have data from some distribution with a mean and a variance. If I want to do inference on the mean, null hypothesis that the mean equals a particular value, alternative hypothesis that the mean does not equal that value, say, then the statistic is familiar now. Wald statistic. Estimate the parameter. If the parameter is mu, my estimate of mu, my MLE of mu, is x bar. Under the null, the mean is mu 0. And what do we know about x bar? X bar is a sample mean for which we know the mean of x bar is the population mean, and the variance of x bar is the population variance divided by n, sample size. Making my Wald statistic, I need estimate minus null value, and I need to divide by standard deviation of the estimate. The variance of the estimate is sigma squared over n. We don't know sigma squared, so we could estimate this as s squared over n, where s squared is the sample variance. And that's what we put over here. So standard deviation of x bar would be the square root of this thing. The estimate is, so I'm going to say s over the square root of n. And this, again, is, if the null is true, standard normal. So we would go to the standard normal. Here's a picture, horrible picture of the standard normal. And we would put our statistic value. Suppose we saw a statistic value of 2.4. We would put that 2.4 up here on the sampling distribution and compute the area under the curve to the right. 2.4 or even more unlike the null. We would also, because it's a two-sided alternative, want to look at the left side, minus 2.4, or even more extreme that way. That would be the p-value. Okay. So when we go, this was one proportion, one mean. When we go to two proportions or two means, It's the same idea. It's a Wald-style statistic. Let me briefly write down what we have here for the two proportions. P1 and P2. So we might have incidence of an adverse event in a clinical trial for the men, P1, and incidence of adverse events in the clinical trial for women, P2. And we might want to do inference. Is there a difference in those incidence rates? Okay, so suppose we want to test the null hypothesis that they are not different. Their difference equals 0. Versus the, again, we'll do two-sided alternative, that they are different. Okay, so if that's our approach, we have, again, MLEs, P1 hat, and we know what they are. P1 hat would be the sum, I equal 1 to N1 of X, let's call it 1I, because this is group 1, the I individuals in group 1. And P2 hat would be the same thing for the second group, the second comparison group. I'll let both of them have their own sample sizes. Call these X2I, MLEs. Then the Wald-style test statistic looks like, again, estimate minus null value over SD of estimate. The parameter of interest right now is this, which is a difference of proportions. How would I estimate that with a difference of my sample proportions? Estimate. Subtract off what we think the parameter of interest is under the null, in this case 0, and divide by the standard deviation of P1 hat minus P2 hat. The standard deviation of a difference of independent random variables is the sum of their individual variances. I'm not going to ask you to prove this on the exam or anything. This is something you could look up in the back of a book to remind yourself how t-tests, what the actual formulas are. But what we have in the denominator, the variance of P1 hat would be estimated as P1 hat 1 minus P1 hat over N1. And the variance of P2 hat would be estimated as P2 hat 1 minus P2 hat over N2. And in the denominator of your test statistics, your Wald statistics, goes a standard deviation, not a variance. Because when we standardize a random variable, we subtract its mean and we divide by its standard deviation. Here's yet another Wald-style statistic. And with a large sample size, we have that result that MLEs are approximately normal. So if the sample size is reasonable here, so we'll say we have a large sample size for each group, N1 and N2, then we again have, under the null hypothesis, a standard normal random variable. We're out of time, but what would happen if the extra detail when we deal with means is right here. I have x bar minus mu 0 and then divided by that s over the square root of n. There's actually a detail that's hidden from you right here that would say, unless you have a really big sample size, you really should be using not the standard normal, but a t-distribution. May or may not tie that together on Friday. I think you've seen these things before. I just wanted to give you kind of I think it's useful, it was for me at least when I first learned it, to see these different test statistics. They all have a similar form. They're doing similar things. It's this maximum likelihood which enables Wald tests. Okay, so any questions on that? If not, I'll let you go and see you Friday.